What's up, everybody? Dr. Gooden here to talk to you about one-way ANOVA. Now, in this video, I'll describe the differences between an ANOVA and a t-test. We'll look at why an ANOVA is so well suited to comparisons between more than two groups, and we will calculate an F statistic by hand. Now, if you stick around to the end of the video, I'll also talk you through what a post hoc analysis is. I'll give you two different ways to adjust your alpha level in order to control for family-wise error. And lastly, we will take a look at effect sizes that you can calculate to determine the practical significance of the difference between your means. I'm Dr. Jacob Gooden, professor of kinesiology at Point Loma Nazarene University. Now, as I mentioned in the intro, this is a lecture all about ANOVAs, and it's a full-length lecture. By the end, you should understand the ins and outs of one-way ANOVA so that you could calculate an F statistic by hand. You'll understand the signal-to-noise ratio that an F statistic is. You'll know how and when to use a one-way ANOVA depending on your research design, and you'll know how to perform a post hoc analysis along with a calculation of effect sizes. All right, now let's dig right into the material. Now, this information comes from the textbook Statistics and Kinesiology, put out by Drs. Vincent and Ware, and it comes from chapter 11. Now, ANOVA is used to determine differences in three or more groups of data, and it stands for, as you can see in the title, Analysis of Variance. Now, it's similar to a t-test, which only tests differences between two groups, and a t-test, remember, it looks for differences between the means, so between the means of two groups, and then it compares that to differences expected due to chance alone. ANOVA uses a similar logic in order to compute the F statistic, but instead it examines the means of three or more groups by comparing variability between the groups with variability within the groups. Statistically speaking, ANOVA tests the likelihood that samples came from the same population. This is why we look at between and within groups variance. So between groups variance is how groups differ about the grand mean, which I'll explain more later in this lecture. And within group variance looks at how scores in each group vary about their own group mean. So we're really comparing how far each of these groups lies from the grand mean, the mean of means, right? All of these groups, if you take their averages and you average those, you get the grand mean. How dispersed are these groups from the grand mean? And then looking within the group, how dispersed are the individual scores surrounding that group mean? Now, taking these two types of variance, we can compute the F ratio. The F ratio is average variance between groups divided by average variance within groups. And F stands for Fisher. It's named after Dr. R.A. Fisher, who developed this technique. Now, recall that in inferential statistics, we are really testing the null hypothesis. We're testing whether the null hypothesis is not rejected or rejected. Now, the null hypothesis states that the ratio of between and within variance will be 1. Right? So they will be the same. Now we can think of F as a signal to noise ratio. So signal over noise. And the reason we can think of it that way is because the signal is really the difference between those groups. It's how far away from the grand mean do each of these groups lie. And the noise is the spread, the variance of each of these groups. If there's a ton of variance, then it's really hard to tell, like, well, even though the mean's down here, you have some outliers up here and some down here. There's a lot of noise to deal with, and we can lose the signal. So either a stronger signal or less noise will result in a larger F statistic. And that's similar to the T statistic that we've calculated before. But in that case, we used the mean difference instead of the mean squares between, and we put that over the standard error of the mean difference instead of the mean squares within. Now, speaking of similarities to the t-test, the distribution, the F distribution, is actually quite different. Now, it's more similar to a chi-square distribution where you have this positive skew. So the reason why an F distribution is positively skewed like this is because you cannot have a negative variance. So mean squares, between and within, remember these are variance calculations. So if variance is not negative, then your entire distribution will be positive. Conversely, the t-distribution, which is like a normal distribution but with larger tails, it in the numerator has that mean difference. Now, if the mean difference is negative, then of course we're going to end up on the negative side of that distribution. If it's positive, then we'll be on the positive side. And so the t-distribution is more symmetrical. Now, another thing to specify is that we're talking right now about single factor ANOVAs. So one-way ANOVA, single factor ANOVA, simple ANOVA, these all mean the same thing. And what they're talking about is the fact that there's one independent variable in this analysis. So the independent variable is the variable that divides your samples into different groups. So if we are looking at, let's say, the vertical jump height achieved, the average vertical jump height in different sports, the sport would be the grouping variable, right? You have volleyball players, soccer players, basketball players, football players, and maybe you want to know who has the greatest vertical jump height out of these 4 groups. And you could use ANOVA to determine that. If any group was statistically significantly greater than any other or less than any other, ANOVA will tell you that. Well, really, ANOVA will tell you if there is a difference statistically, and then you'd have to go into your post-hoc analysis. But anyways, sport there would be the independent variable. Another example could be, let's say in kinesiology, you're testing 3 different types of aerobic training programs and seeing which one has the greatest impact on aerobic capacity. So the type of training in that case would be your independent variable. It's what the researcher controls. And then the aerobic capacity, however you measure that, hopefully VO2 max or some correlate, that would be your dependent or your outcome variable. So let's run through an example. And in this example, we will use arbitrary numbers without units just to make the calculations more simple. But let's say that we are comparing strength scores in 5 different groups. Okay, each of these groups is given a different 6-week training program. So maybe there's free weight strength training, maybe body weight, sort of calisthenic training. Maybe we have hill sprints as another group, maybe resistance bands for another one, and then Pilates, and then a control group, right? So that's 5 different groups, and we want to test their strength levels at the end. Now, probably a tighter research design would be to test their strength levels before the training and after the training, so we can get the change and we can look at the change in strength, because we know that we could get different levels of starting strength just due to random variation in our samples. But in this case, we'll assume that all of these subjects come from the same initial population and that any differences are only due to the training, right? Just to keep it simple. So 5 groups, each with a different type of training, and we're going to test their strength levels. Now, the null hypothesis posits that all of the means of these groups are the same. There's no difference between them except for what would be expected in the random error, in random sampling error. The alternative hypothesis is that at least one of these groups is not equal to the other groups. Now, in this case, why would we not just run multiple t-tests? And we've talked about t-tests before, and they're great for comparing 2 different groups and seeing if there's a statistically significant difference in those means. Well, in this case, and in most cases where you might be tempted to run multiple t-tests, the reason why you don't is because you run the risk of increased type 1 error. Now remember that type 1 error is a false positive. I'll just go ahead and write that down. False positive. This is when you find an effect or you find a difference that is not actually a true difference. It doesn't actually exist in the population. Or in this case, both of these samples come from the same population, but you've determined that they come from different populations because you're saying they are significantly different, when in fact they're not. So this will depend on the alpha level that we set, but let's say that we set it at 0.05, like the vast majority of research, at least in the kinesiology field. Now our risk of type 1 error is 5%. Type 1 error rate equals the alpha level. But if we run 2 t-tests, then we roughly double our error rate. And with each t-test that we run on the same data, right? If we run it on different data, that's okay. But if we're running it on the same data, then we increase our type 1 error rate every time we run another test. Now, technically, it's not as simple as multiplying the alpha level by the number of tests, really there's what we call a family-wise error rate, and you calculate that as 1 minus alpha raised to the c power, where c equals the number of comparisons. All right, so you raise that to the c power and then you subtract that from 1, and it will be pretty close to the number of comparisons times alpha, but slightly less. So for example, if we have 4 groups and we want to compare differences between each of these groups, that is a total of 6 comparisons, and we end up with a 26% chance. We're running a very high risk of type 1 error rate. So 26% chance that we make a type 1 error, and that's just too high. That's 1 out of 4 times that you run a t-test, you're going to be getting a false positive. Now, another reason not to run multiple t-tests is that a t-test does not use all the information. A t-test uses variability data from just 2 of the data sets being compared, and that's not a problem at all if you only have 2 data sets to compare. And ANOVA, on the other hand, factors in all of the variability information from all of these data sets together when computing the F statistic. Oops, I accidentally crossed that out. Pretend like I underlined that. And then lastly, it's easier to do one ANOVA test than multiple t-tests. As you can imagine, let's say that you have 10 groups. It's going to be really confusing to keep track of all of the t-statistics and the resulting p-values when you compare group 1 to 2, 1 to 3, 1 to 4, etc., and then 2 to 3, 2 to 4, 2 to 5, etc. That's a lot of t-tests, right? And so running one ANOVA will tell you either yes, there's a difference somewhere in these groups, or no, there's no difference. And if you get a non-significant F value, right, an F value that is not greater than the critical F, or if you're doing it with statistical software, a p-value that is greater than your alpha level, then your analysis stops there, and it's much more simple. Now, before we run ANOVAs, we have to make sure that our data meets a certain set of assumptions. The good thing about ANOVA is that it is a robust statistic, meaning that even if you violate some of these assumptions, what we can do is we can make our alpha level, our alpha criterion, more stringent. So maybe take it from 0.05 down to 0.01 to decrease our chances of running a type 1 error. So here are the assumptions. We need to ensure independence of scores. So the scores should not be related to scores in any of the other groups. They need to be independent groups. Usually in kinesiology, this is ensured because you are measuring different people in each group. We also want our dependent values to be somewhat normal, right? If normality is violated, then F is larger than it should be, the resulting P is too small, and our type 1 error risk increases, so it's greater than our alpha level. Thankfully, as I said, ANOVA is robust to violations of normality, and we can correct for it by evaluating F at a lower alpha. So just being more strict and conservative with our inferences. Now, another assumption of ANOVA is homogeneity of variance. Remember, homogeneity just means to be the same across the board. So we need the variance in each of our groups to be roughly the same. Now, a good rule of thumb is that the variance in any group should be no larger than 2 times the variance in the smallest group. So the group with the greatest variance, if that variance is greater than 2 times that of the smallest group, then you're kind of getting a little bit of a red flag. Now, you have a serious violation if the ratio of the largest to the smallest variance is greater than 9. So really, your data is great if it's 2 to 1, but if it's 9 to 1, then you're getting into some serious problems, and then you really have to either take your results with a grain of salt or consider not running an ANOVA, doing something different. Maybe consider transforming your data somehow, or making your alpha level much, much more stringent. Now, in kinesiology, this is rarely checked or reported, but as future researchers, as people who want to uphold a strong level of scientific inquiry, it's really important that we do check our data against these assumptions and report any violations of these assumptions if there happen to be any. Okay, so how do we calculate an F statistic? We need to determine the between and within group variance. So between group variance is how the group means differ from the grand mean. And I'll draw this graphically for you. Let's say that this dotted line is the grand mean. And pretend that we have three groups. Here's the mean of one group, here's the mean of another group, and here's the mean of a third group. So the variance would be the vertical distance between each mean and the grand mean. If these means were farther apart, that variance would be greater. Now, the within group variance is how much individual scores deviate from their own respective group means. So let's take the first set of three that I drew here. Let's say that in group 1, we have not much variance. In group 2, we have a lot of variance. Sorry, those are lines. I'm trying to draw dots. And in group 3, we have almost no variance at all. All right, so that's what it looks like to have different levels of between or within group variance. Now, it's important to know that within is usually specified by W, but it's also interchangeable with the word error, or specified by an E. Okay, so within group variance or error variance, it means the same thing in the case of ANOVA. Error doesn't mean that there was a mistake on the part of the researchers or on the part of the participants. It just means that that's the amount of variance within the group, and the larger that variance is, the more kind of noise there is through which to see that signal of the between group variance. Now, the total variance in the system would be the between group variance plus the within group variance. Okay, so how do we get from the variance, the within and the between variance, to the F statistic? Well, first we have to compute the sum of squares, and then we have to turn that into a mean squares, and then we take the ratio of the mean squares between to the mean squares within, and that is our F statistic. All right, so let's take a look at these formulas. The sum of squares is x, or the score, minus the mean squared, and then you sum all of those, right? So it's the sum of the deviations from the mean squared. Now, specifically, to do this within the group, you look at each individual score and you subtract the group mean. To look at between groups, you take that group mean and you subtract the grand mean. Remember, in that graph that I drew with these different group means and the grand mean, between, sum of squares between is looking at the distance here between the group mean and the grand mean. The sum of squares within, on the other hand, let's say this is a score, these are all scores around this mean, it's looking at this distance between each score and the group mean. If you wanted to directly calculate the sum of squares total, you would take each score and subtract the grand mean. Or remember, you could also just add sum of squares within and sum of squares between. Now, if this is confusing to you, just remember that it's confusing to everyone. And all we're trying to do is calculate that signal to noise ratio using variance. And we're just doing it in a specific way, looking at the between group to the within group variance. Now, once we've calculated the sum of squares, we have to turn them into mean squares, which is essentially like a standardized version of sum of squares. And we standardize the sum of squares by the degrees of freedom. So the within degrees of freedom is equal to the total sample size minus the number of groups. So K equals the number of groups. And we already know that uppercase N equals the total size of the sample. So in our case, if we have 5 groups and we have 35 total subjects, and that's 35 minus 5 equals 30 degrees of freedom. To calculate degrees of freedom between, we take the number of groups and just subtract 1. So that would be 5 minus 1 equals 4 degrees of freedom. Okay, now we're almost there. Now we calculate mean squares by dividing the sum of squares by the degrees of freedom. Okay, and we need to make sure we divide by the correct degrees of freedom. And then finally, we take the resulting mean squares between and put it over the mean squares within. Phew, all right, so that's how you set up the equations Now let's do it with our actual data. Don't worry, I've already done the calculations, so this should go a little bit more quickly. Here's a set of fictitious data looking at the strength values of these 5 different groups, one of which is a control group, so they didn't do any strength training, and these other 4, they did different types of strength training, and we tested their strength values after 6 weeks of training to see if there was a difference between them. Now we've already calculated the sum of all scores. We've got the number in each group, which is 7 across the board, and then we have the mean of each of these groups. And it looks like right off the bat, just by eyeballing, that group 2 has the greatest mean, followed by group 4, then group 1 and 3 and 5. Okay, so we might, just by looking at these, we might say, well, it looks like group 2 had the greatest gains in strength, or rather was the strongest after their training. But we want to know, is that a statistically significant difference, and are there differences between these other groups? Okay, so the first step is calculating within group deviations. So first we subtract the mean of each group from the score, and that's how we create this table. So these values were derived by subtracting the respective group mean from the previous table from the individual score. Okay, we get those deviations, and then we square them, and then we add all of those squares together, and that gives us the sum of squares of each group, each individual group. And then we do the same thing between the groups, right? And remember, between group sum of squares, we start by getting the deviation of each individual group mean from the grand mean. We get those differences here, and then we square them and sum them all up. Now, once you add up all of the sum of squares of the individual groups, which are right here, you get 47.37, and that is your sum of square error, or your sum of squares within groups. Now, to calculate the sum of squares between, we take the 7.26 that we already calculated and multiply it by the total number of data points in each group, or the sample of each group. And that's just because we have many more data points contributing to the sum of squared error than we do contributing to the sum of squares between. So we'll multiply that by the number of individuals in each group to get 50.82. Then we take our degrees of freedom calculation, which we already looked at as being 4 and 30, and we divide the sum of squares by the degrees of freedom, and we get about 51 divided by 4 and about 47 divided by 30, and that gives us 12.71 over 1.58 for our F statistic, which comes out to 8.04. All of that work to get an F statistic of 8.04. But what does it mean? To find that out, we have to look at a critical F table, or an F distribution table. Now, in this table, this is similar to a T table. We are looking at degrees of freedom in the numerator along the top and degrees of freedom in the denominator along the left side. Okay, so we remember that we have 4 degrees of freedom in the numerator because we had 5 groups. And in the denominator, we had 30 degrees of freedom because we had 35 subjects minus 5 groups equals 30. Now, if we want our alpha level to be set at 0.05, right there, we could also choose, 0.025, 0.01, 0.001, but we want 0.05. We're going to go over, and the critical F value is 2.69. So this is the F value that our F has to be larger than in order to declare that there is a statistically significant difference at the alpha level that we have set. We set it at 0.05, but look, all the way down to 0.001, we have still a larger F value than that critical F. So 6.12, we have a larger F. So we can determine that our p-value then, the probability that our results are due to chance alone, given that the null hypothesis is true, that is less than 0.001. Now, our resulting ANOVA report would read like this. We want to report the sum of squares, the degrees of freedom, the mean squares, the F statistic, and the p-value, and we've already calculated all of these. So we have sum of squares between, within, and total. We have the degrees of freedom between, within, and total, and then mean squares between and within, the F statistic, and our p-value less than 0.01, 0.001 actually, because of the table that we used went down to that next level for the alpha level. Now, if you were calculating an f-statistic and p-value using statistical software, then we can determine an exact p-value. And in reality, this is what you will be doing the majority of the time. So in this case, the exact p-value would be 0.0002. Now, when doing this by hand like we just did, even if you're using Excel to do the calculations or some other type of computing software, if you're using the definitional formula to calculate these by hand, you have to look at the critical F value in a table in order to determine whether you can reject the null hypothesis. However, most statistical software that you use, I would guess all of it actually, will give you a p-value and calculate that for you automatically. It will give you a specific p-value, and if the p is less than your alpha, then you can reject the null hypothesis. Now, just because you got a large F value and a significant P value, that doesn't mean you know which groups are significantly different from the others. To do that, we have to move on to a post hoc analysis or post hoc follow-up testing. Now, typically in post hoc analysis, we use what are called pairwise comparisons, and this is where you just compare all the different groups to each other. You can also run planned comparisons, which is where you specify beforehand, before you collect the data even, which comparisons you are interested in, and then you only run those comparisons. And that can be advantageous because, as you'll see, you won't have to adjust your alpha level as much to control for family-wise error rate. You can also do things like combining certain groups and comparing the combination of those groups against another combination of groups or against another single group. For instance, maybe you want to compare all 4 treatment groups against the 1 control group, and something like a Scheffé post hoc analysis would allow you to do that. In this video, we're going to talk about two different post hoc analyses. One is a Bonferroni adjustment, and another is a Tukey's or 2Ks. I don't really know how to pronounce it. I think most people say Tukey's. Honestly, significant difference. All right, so the reason that we do these adjustments to the alpha level is because we want to control the family-wise error rate. Remember previously I said the whole reason we don't run multiple t-tests is because we don't want to jack up that type 1 error rate so that we have all these false positives. And if we're doing all these comparisons, now that we have a statistically significant F value, then we really do run a risk of inflating our type 1 error. So the first type of adjustment is called a Bonferroni adjustment, and it's a fairly common adjustment to use. However, it is a pretty conservative adjustment of your alpha level. And all you do is you take your alpha level and you divide it by the number of comparisons, C. So let's say that you were to make 5 comparisons and your original alpha level was 0.05. Well, now your new alpha level is 0.01. So during your planned comparisons, when you're comparing the differences between each of these groups, they have to be significant at a more stringent level, right? So now instead of 0.05, now it's 0.01. Let's say you had to make 10 comparisons. Well, now your alpha level is 0.005. Okay, so it just becomes more strict. There's much less likelihood of type 1 error, false positive, when your alpha level is so low. The problem is you run into a greater risk of type 2 error, which is a false negative, which means you don't reject the null hypothesis when in fact it should be rejected. Now, a slightly less conservative approach is Tukey's honestly significant difference. And what we do here is we calculate a raw score mean difference. So we calculate a certain mean difference that must be attained to declare a significant difference between any 2 groups. Okay, so first we group the means in order of magnitude. And so we see here group 2 has the greatest, followed by 4, 1, 3, and 5, as we've already identified. And then we determine a Q value from a studentized range distribution for K, a number of groups, and the degrees of freedom within, or error. Now, I'm not going to show you exactly all of these calculations in this video because honestly, the majority of the time this is run with statistical programs like Excel or like SPSS, but I do want to explain more or less the way that we are controlling for family-wise error rate, because that is important to know. we take the mean square error from the analysis that we already conducted, and n is the size of the groups. If n is not equal, we have to use a special equation to account for the different n between the two groups that we're comparing. So in our case, if we look at a studentized range distribution, we get Q as 4.1. We have our mean square error as 1.58, as we already calculated, n equals 7, which is the same in all the groups, and we get a minimum raw score difference of 1.95. And so what this is saying is that any difference between two groups that is greater than 1.95 is a statistically significant difference. And so when we examine our groups, we see that group 2 is greater than group 1 and 3 and 5, because the mean difference between group 2 and all of those other groups is greater than 1.95. Now, we've talked about what a one-way ANOVA is, we've talked about what an F statistic is, we looked at how to calculate an F statistic, then we calculated one, and we looked at a post hoc analysis, a couple different ways of doing it. Now we have to talk about effect sizes, and I'll show you a couple different ways to run effect sizes and what it actually means for your analysis. So the first measure of effect size we'll look at is eta squared. Eta squared is actually similar to R squared that we looked at when we examined correlations earlier in this course. Now you can calculate R squared by taking the sum of square between and putting it over the sum of squares total. And what it represents is the percent of variance accounted for in the dependent variable by the independent variable. So in this case, we get approximately 52% of variance in strength is accounted for by the treatments employed. Okay, so the different treatments across the board and the no treatment in the control group, those different treatments account for 52% of the strength variance, and that's a pretty big amount of the variance. Now, a slightly more accurate way, but a little bit more complicated way to calculate this is with omega squared. Omega squared tells us, in this case, that 46% of the variance in strength is accounted for by the strength training programs. Okay, so omega squared is a little bit more accurate, it tends to be, and it's usually a little bit lower than eta squared. However, both of them are measures of the variance accounted for by the independent variable. Okay, now I understand that was a lot to digest. We went through what a one-way ANOVA is, we talked about the logic of an F statistic, we calculated an F statistic, and we did a post hoc analysis in a couple different ways and looked at some effect sizes. Now remember, one-way ANOVAs are used when you have a single independent variable and you have 3 or more groups of data, and you're interested in comparing differences between those groups of some dependent variable. Now I showed you how to do this by hand, but most of the time you'll be doing this in some sort of stats program. So go ahead and select your stats program of choice, whether it's Excel or SPSS, or who knows, in the future maybe I'll do a video on R or JASP, and I'll see you in that video and show you how to run an ANOVA on a simulated data set to show you just how easy it is to compare mean differences between multiple groups. All right, guys, thanks for watching. If you had any questions, let me know down in the comments, and as always, I'll see you on the next video.